Okay, let's go to look at ROC curves. And again, we did look at ROC curves earlier in the semester, so I've already kind of like started warming you up on this idea of a ROC curve. Remember the bombers leaving Germany to go over to England? And you know, there's an old show, an old video of the guy on the English air base who has to ring the alarm bell to launch the British fighters. So when the radar would show the Germans are coming in the bombing, his job was to go over and run the siren, and then the pilots would go get into the fighter, pilots get in their planes and go try to shoot the Germans down. It was interesting. In the video I watched, the guy sitting there drinking his tea. Classic British. I went to Britain on my mission. They love their tea. Okay, he's sitting there and drinking his tea, and then he gets a phone call and says, you know, they're coming. So he gets up and he strolls, and then he does the siren. Now, if that had been me, maybe I'm a little too keyed up. Maybe he's right, but I would have run over there and done the siren. But it was a classic Brit. I just loved it. He drinks his tea and then he goes and sets off the alarm. It's fun. Anyway. So again, the idea with that is if he scrambles those pilots and there are no bombers coming in, what happened? He just spent a lot of money, and these guys were already very tired. If you know the story of the Battle of Britain, the pilots there were so few pilots left that they were working like 21 out of 24 hours flying. There were so many bombers coming in. These guys would go off and they would fight off the fighters, and those that survived would come and they would just fall asleep. They'd land their planes on the land, and they would just fall asleep in their planes. And then when the air raid siren went again, they would just wake up and go. I mean, it was just amazing. And Winston Churchill said, never have so many owed so much to so few, because those men in the most terrible conditions basically saved the war. You know, it was amazing. Heroism. Wow. Anyway, so basically the ROC chart was designed so that you would have all of the true positives. So in this case, let's just assume, for simplicity's sake, let's assume that there are 10 true positives in that table. And let's assume that there are 5 false positives in the table. So if I'm looking at my probability table, there's only 15 records in there. 10 of them are true positives, 5 of them are false positives. We don't care about negatives. ROC curves don't even look at the negative side of the table. They just look at positives. I just want to know how well I'm doing with calling a bomber is a bomber or not. You know, how many times am I right relative to how many times am I wrong? So in this case, what happened is the very first record that we looked at was a true positive. And so 1 out of the 10 true positives, that's 10% from 0 to the top. So our true positive, the first correct sighting of the bombers, the second correct sighting of the bombers, that's another true positive. We kept correctly sighting the bombers for the first 6 things that we saw on the radar screen. Okay? And then we thought it was a bomber, but it was a flock of seagulls or a cloud, you know, whatever gives radars false positives. Okay? Then what happened there is, as soon as we hit false positives, then it starts moving that way. Okay? Whichever proportion. Now, if there were only 5 false positives, which is 20%, then that line would have gone over 20%. Because that would have been, if that was only 5 false positives, that line would have gone over 20% of the way of all the false positives. And then it would sit there. And then the next one would be, if it was a true positive, it goes up. If it's a false positive, it goes over, and so forth. And so basically what's happening is, can you see that this is a representation of how well we're doing at getting true positives relative to false positives? It's a way of putting it on a chart. And you can just see, I'm right, I'm right, I'm right, I'm wrong. I'm right, I'm right, I'm wrong. I'm wrong, I'm wrong, I'm right. You know, whatever. And then you take all that area under the curve and you add it up. Now, random is under it isn't the base rate. If we just were randomly guessing, then we'd be right 50% and wrong 50% of the time. That's what that diagonal, there's the word I was looking for. The diagonal line is just random guessing. And so you'd be right 50% of the time and wrong 50% of the time. but we're smarter than random guessing, and so we're going to have greater than 50%. So above the diagonal line is what proportion of that 50% are we right, and what proportion of the 50% are we wrong, okay? So it's showing, it's from an area visual standpoint, it's just how well are we doing. Now what do you want? You want to hit every single true positive before you even hit one false positive. If you're dead perfect, remember when we had all the mushroom data and it was so good that we could be right 100% of the time? In that case, the blue line would go all the way up to 1 before it started going to the right. We found every single true positive. So in that case then, if it was perfect, the blue line wouldn't have marched to the right. It would have marched all the way up here, and then it would have started marching to the right, and then under the area of the curve would have been 100% possible. We got everything, okay? So that's a perfect classifier. Perfect, we never screwed up. Every time we said it was German bombers, it was, every time. We never got tricked by a flock of seagulls or a weather formation. Here we're getting tricked. Here we're hitting some false positives, yeah.
So the red line is random, it's not the naive.
That's right, it's not naive.
Would be if there was 10 bombers, like there was 100 detected objects or whatever, it'd be 10 out of 100.
Yeah, exactly. The naive rule is based off of that base rate. Okay. And this is just random probability is the 50-50 thing. You know, it's like throwing darts. Is that a bomber or not? I don't know. I'll call it one this time, yeah. But, you know, I'm not smart. I'm just making random calls.
Do we ever use random as a base or anything? Like, obviously you showed it here, but do we ever, like, is that useful?
No, because we hate it.
Okay.
Because we just, yeah, that's exactly. We use the base rate in the context of the lift rate, which let's talk about that next, because that's the last thing we need to talk about today. Yeah. So let's talk about that, because there's one homework question. You need to know this, and there'll be some questions on the midterm on this too. So let's talk about lift charts, okay? If we take this data, let me roll this back now. If we take this data, which is our little probability table, if we take this table and we take the top 10%, now in this particular case, what we have is what's our base rate here? How many? In this case, we have 50% are trues, and we have 50% that are negatives. So our base rate is 50-50, right? Our naive rule wouldn't help us at all here, because we would just estimate that half of them are positive and then we'd be wrong half the time. So that's as good as our base rate will let us do, okay? But if I look at the top 10%, there's 24. So let's just for simplicity, let's look at the top two. Our top two is we're right 100% of the time, okay? But our naive rule says by random guessing we'd be right 50% of the time. So basically in the top two, we're right 100% of the time. So we're twice as good as random guessing, right? So basically what lift is how much better can you do from random?
But I thought it was compared to the base rate though, as far as like the base rate being, so say the 10%.
Oh, it is. In this case, the base rate's 50%. Okay. Thank you. Let's make that clarification to make sure it's not confusing people. It's an important. So basically what you're doing is you're saying relative to the base rate, it just so happens that the base rate in this case is 50%. How much better than the base rate are you doing? That's right. So if the base rate, let's use a different example. If the base rate had been 20%, okay, and we're right 100% of the time in any decimal, then we're 5 times better than the base rate. Okay? So what it does is it gives you, what it's saying is, how many times better or worse than the base rate are you because you're smart, because you use your machine learning algorithm? Well, in this case, we're twice as good as the base rate because we're 100% right in the top decile, where if we were just using the base rate, it would be 0.5. So we're twice as good as the base rate. So if we had a 0.4 base rate and 100% accuracy, 100% in a decile, what's our lift? So let's say I pick a group of records. And I'm right 100% of the time, and the base rate is 40% of the time. What's the lift? Yep, 2.5. So the base rate into whatever I'm getting in any decile is going to give me my lift. So this is lift. So in the exam, I'll say something like this. There's 3 or 4 of these problems on the exam. I'll say, pick out the top 5 records and compute the lift. Now, the top 5 records, we're 100% right in the top 5 records. So that's 100%, okay? The base rate is 50%, so 100% over 50% is 2, so our lift is 2. Yeah, we're right every single time in that top 5 records.
If the red 0 was in it, then it would be...
It wouldn't be 2.
80%.
Yeah, exactly. So in that case, well, let's do it, okay? In this, let's take this first group of records then. We're right 10 out of 12, all right? So in that, the decile is, don't get hung up on the decile. All the decile thing does is it makes it easy to grab from the probability table the 10% that are most likely to be what you're looking for. Then the next 10%, they're the most likely, because they're the 0.1, they're the ones, 0.99, 0.999. Those are the most likely to be what you're looking for. And so decile's easy because you can just do it by 10%, the top 10%, the next 10%, the next 10%. But you can apply it to as many of the records as you want. Let's take, these are the top half of the records that are most likely to be things that we're looking for, okay? And we're right 10 out of 12 times. 10 out of 12. And let's see, that's 5, 6, what is that? 0.83, something like that. 0.83 if my math is, I'm just quick and dirty math. Our base rate is 50%. And so our lift here is going to be 1 something, 1.3, something like that. Is it 1.7? Someone do the real math. I can't do that one in my head. Is it 1.7? Okay. That sounds about right. I think just quick and dirty, it looks right. Okay. So you see what we're doing? So we're just taking a block of records, whichever block we choose. I could have taken the top 10% or the top 20% and said, what proportion of the time are we right in that group, whatever it is, divide it by the base rate, and that's your lift. And the lift is how much better than the base rate am I because I'm smart, because I used a machine learning algorithm. Okay? Yes?
Sorry, so the base rate, is that just like if you had no sort of concentration at all, how likely would you be?
That's right. You just look at the data and say what proportion it dominates. That's right. And I'll just apply that to everything, which is terrible. Yeah.
It's just the naive rule.
It's just, yeah, based on the naive rule. That's right. It's applying the naive rule. Exactly. And here we're saying, how much better than the naive rule do we do? We're 3 times better. Okay. That's pretty good. You'd like it to be even higher. Now let me show you one where you can see it's kind of interesting what happens, because what happens is at first you're above the base rate. So at first what happens is, remember, in the top 10%, these were the ones that were most likely to be what you're looking for, and we're doing 3.2 times better than the base rate, 2.4 times better than the base rate. We match the base rate. That's as good as random sampling, but think about it. Over here is the ones the most likely to be, according to our algorithm, these are the most likely to be the characteristics of interest that we want. These are the most likely poisonous mushrooms, because it sorted it from ones on down, the most likely to be the characteristic of interest. So, and we're right, we're doing better, and then we get down here, and then here we drop below the base rate. But why are these higher than these? Because our algorithm was smart and it helped us find the poisonous mushrooms, and then we could drop down below 1 in the base rate. And one of the reasons why this is low is because the cream got bubbled to the top. Our algorithm did its job, said the poisonous ones are in the top decile and the next decile and the next, and then we get not as good until we finally can only do as well as the base rate, and then over here we'd be doing less than the base rate. So you might stop. You might say, well, I'm only going to take the top 40% of the records and use those because I'm not even doing the base rate over here. You know what I mean? It's a way of kind of making sense of when to stop when you're using your estimates.
Would it ever be valuable to
No, because you're even worse than the base rate then. Because what's left is there's not very many poisonous ones in the remaining 60% of the records. So if you use the base rate, you're going to, yeah.
Is that good for the lift? You're using the true positives and not the true negatives. You're only looking at the times where it was poisonous and you guessed that it was.
Yes.
That's why it
Yep.
measures off.
Yep. That's why.
So even though you're right when you say that it's not poisonous and that it's not, we're not
That,
even interested.
this doesn't visualize that. This just visualizes how often you're right relative to the base rate. Yeah. How are we doing? Did the concepts we covered today in class, did they kind of make sense? Precision and recall and lift and ROC charts, a way of thinking about these categorical things. And so I give you some homework questions for you to work with the ideas a little bit, and there'll be a bunch of exam questions. But this is so bread and butter. This is so fundamental. We'll just use it every day. You know, every time we do a categorical algorithm, we'll look at recall and precision and accuracy and error rate, and we'll look at the F measure, and we'll look at the ROC curve, and that's just our bread and butter, how well we doing stuff. You know what I mean? So if you understand this, then it's just kind of like, oh, okay. I know when I get an area under the curve of 0.89, I know what that means now. It's not just some random arbitrary thing. It's just I went up when I was right, and then I went to the right when I was wrong, and now it won't be some arbitrary thing. It'll be something that means something to you. Okay. Now, after today, we're going to get back to algorithms again. So we'll get back to start doing logistic regression, which is a fun topic for next time too. So, okay. Thanks.
So if I'm understanding this right, so this is comparison to the base rate. So,
Right.
So for this 3.2%, so basically you can predict for these 16 responders 3.2% better than the base rate. Is that how we're interpreting it?
Yeah. So basically in here, you're picking out 16 responders out of 100. So your proportion of being right is 16%. Okay. And the base rate is 5%.
Yeah.
So you're 3.2 times better than the base rate. So what you're comparing is this response rate, which is your proportion of being right in that top 100 records, to the base rate.
Okay.
Exactly right.
So for the homework, the base rate is this 65 divided by 1078 because
Okay.
we're trying to predict the fraudulent records. Am I understanding that right?
Uh-huh, yep.
Okay. Sounds good. Thank you.
Yeah, you got it. Good. Hey, guys.
I'm signed up. I'm planning on taking the LSAT the same day and time as the in-class exam.
Okay.
Should I meet up with the TA to take it beforehand proctored, or?
Why don't you let's set a time where they can just proctor it after that day. The university says we're not supposed to offer them before. We'll just offer it after. No big deal. So when we get closer, then just set up a time with the TA. I'll make sure he has an exam. You know, the TA for this class. Then you can just go in during his office hours and just take the exam. No harm, no foul.
Thank you.
Okay, you bet.
Question on the last graph.
Okay.
So after we know, like after a certain time, we are not very good at the baseline. What should we do after that? It just gives you the concept, like after a certain amount, you.
That's right.
Okay.
That's right. So what you would say is, let's look at another example. People that commit fraud. Okay. So if I say, here.
We can predict fraud.
Yeah.
Good.
Pretty good. And then here
Not very good.
Here it's just as good as the base rate.
Right.
And here it's worse than the base rate.
So like.
But these are the ones that our algorithm says are the most likely to be the fraud guys. So there's less frauds left in these remaining deciles because we bubbled them, sorted them to the top over here on the left. So this just tells us when are we doing worse than the baseline, but it's not that this is bad, it's because there's less frauds to find over here because we figured out and sorted them up here.
Okay.
Yeah.
Okay. Cool.
So
kind of like give you concept like how data distribute throughout the whole data set.
Yeah, this is a way of saying,
So it can be like low here, but very high here because like all the frauds happen after like kind of in the end,
well,
end of the year.
what we did, it's not time. That's not time. It's what we did is we said, let me go look at this chart. What we did is we broke these into deciles. And in the top decile, which is just these two records, we were right 100% of the time.
Right.
So it isn't time, it's sorted the most probable to be frauds to the top. And then in the top two records, we were right 100% of the time. But if you look at the base rate, we're only right half of the time. So we're twice as good as the base rate. But those are also the two that our algorithms was most sure were frauds. When it gets down here, it's pretty sure they're not frauds. And so, yeah, the base rate's going to be low, but it's also they're not frauds. So we bubbled the cream on milk. You know, we take the things that are most likely to be what we're looking for to the top. It's ordered that way. Yeah.